Hydrostatics examples 7, the phenomenon of apparently defying gravity with tubes that are open at the bottom but closed, sealed at the top. So we'll start here with 3 tubes, one completely in the air, one completely immersed in the water, and one that's half in and half out, open at the moment to let air in, but we're going to slam that shut. And then we're going to push this tube down into the water and pull these 2 tubes up out of the water. When we do so, this one having air trapped inside of it, that air is going to be compressed when it goes down into the water here. So we see these 3 cubes of air have been compressed down into 2.5 cubes of air at this point. This middle tube, when the top is sealed and it's then lifted up, the 2 cubes of air trapped inside there, they're going to expand somewhat here at this moment to 2.5 cubes of air, and they will successfully pull some water out with them. This water apparently defying gravity, hanging over this empty space, or not empty, but full of air between it and the water below, lifting up this water with this expanded gas trapped above it. And this last tube, we're going to lift it up and it'll be completely filled with water, and we'll pull all that water up out of our tank here and somehow suspend it above the air below. So how is this possible? I think you can see how it works. The question you'll be answering is, what is the pressure at points A, B, and C? So you'll compute those using these 2 principles, set the pressures equal at points on horizontal lines in a single fluid, and use our difference in pressure between 2 positions as rho, g, h. Pause the video now and work out the pressures at points A, B, and C. Got it all figured out? Okay, here we go. Let's see, at point A, what we'll do is recognize that in a gas, the pressure doesn't change much with height, so the pressure at point A will be the same as the pressure here at this point, 2 meters below the surface. And that will be the same as the pressure, say, over here on that same horizontal line. And the pressure at this location we can find by doing delta P between here and the surface. So the atmospheric pressure plus rho gh for a 2 meter column of water will give us the pressure here at this point. Which is the same as the pressure here, which is the same as the pressure at A. Then for the pressure at B, we'll note that the pressure here at the base of that column of water, it's in contact with the air, so it must match the atmospheric pressure. So we'll do delta P between the atmospheric pressure here and point B. And similarly for point C, the base of that column of water is in contact with the air, which is at 1 atm. So the base of that column must be at atmospheric pressure. Okay, let's then perform those 3 calculations. At point A, our difference gives us a 1.2 atmospheres. At point B, the difference gives us 0.8 atmospheres. And at C, the difference gives us 0.9 atmospheres. So this is our picture then. Our compressed air inside this tube at 1.2 atmospheres, matching the pressure at a depth of 2 meters below the water's surface. This compressed air will be attempting to burst out of this sealed compressed container, since its pressure is greater than the pressure of the surrounding fluids. So those red arrows represent the net pressure force on the walls of that container. Here at point B, 0.8 atmospheres, we're at low pressure relative to the outside. All this gas trapped in here, this expanded gas, has reduced in pressure. Reduced enough so that the pressure difference between the gas trapped in the tube and the outside air pressure, that pressure difference is enough to hold up this 2 meter tall column of water. That is the pressure force from the 1 atmosphere pushing up minus the pressure force from the 0.8 atmospheres pushing down. The difference there is equal to the weight of this 2 meter tall column of water, and the Earth's atmosphere is supporting this water. Likewise here, our 1 atmosphere of pressure here at the bottom is enough to hold up this 3 meter tall column. The pressure inside this tube will go from 1 atmosphere to 0.9 to 0.8 to 0.7 atmospheres at the top of the water underneath the cap on that tube. So in these two containers, the pressure difference outside and inside is going to result in net pressure forces compressing these tubes. Both of these are going to tend to be subject to collapse or implosion since the fluid pressures outside 1 atmosphere are all greater than the fluid pressures inside. How can the air hold up these 3 meters of water? Well, we know, of course, that 1 atmosphere is enough pressure to hold up a 10-meter column of water in a water barometer. So it's certainly strong enough to hold up any amount like this. With that downward pressure on the top cap here, trying to implode it, we're in danger here of of air from the outside breaching through cracks and getting inside that tube, at which point water would drip out the bottom as it was displaced by air bubbles that managed to get inside. This downward net pressure force on the top, that would be the sort of suction that you feel when you're using your fingertip to hold up water inside a drinking straw that you've submerged in water and then lift it out. Lift it out so you can transfer, say, Mountain Dew from your fountain drink onto your tongue, strawful by strawful, as you savor the wonders of science. But as you do so, remember to pay respects to the almighty Earth's atmosphere, whose great upward pressure makes it all possible.